So, what we will do here is to give some more details of the blackboard example. For finding some conditional expectations. What particular blackboard example I am referring to? First I will do the discrete example, right. Well, let me not write 1 or 2, let me just start with discrete example. What discrete example did we do in the blackboard? We did the Poisson example, right. So, let me bring that up again. Y was given to be Poisson with parameter lambda 1. Z was given to be Poisson with parameter lambda 2, right, and y and z were independent. This is very important, of course, otherwise this problem doesn't become solvable. So, y and z are given to be independent. Then we also defined x, x to be y plus z, right, and the problem, the question, let me just say, okay, just let me say problem was find the conditional expected value of, let us say, x, sorry, not x, the conditional expected value of y given that x took the value x naught. So, this was the problem, right. We have to find this conditional expectation, and in this particular case, right. So, I am going to work out this thing in detail because I am not happy with hiding all the details that we or not giving the details in the blackboard example. So, I am going to take work out the steps in great detail. So, let us say solution. First thing, what is the PMF of x here? So, x is, we know that if we add two independent Poisson random variables, the sum is also Poisson distributed. So, we begin with that, right. We need to, first we will identify the PDF of x. Or the distribution, the PMF of x. What is x? X is clearly, or let me write it as we know. I hope we have covered this property of the Poisson distribution, right, in some earlier lecture, but if you haven't, or if you don't recall it exactly, does not matter, take it for granted that if you add two independent Poisson random variables, right, the sum is also going to be Poisson, with the parameter being the sum of the two parameters, right. So, in this case x is going to be Poisson with parameter lambda 1 plus lambda 2, right, we know that. So, this is very important, right. So, which means that, what does this mean? This means that omega x, the set of values that x can take, is basically the entire collection of non-zero integers, non-negative integers. So, basically omega x is the set 0, 1, 2, so on. And so, so x naught can be any one of these numbers, right. So, always the conditioning value x naught, right, must be one of the allowed values that of x, especially in the discrete case, right. So, x naught in this case can be any of these integers. So, we know that, right, we are given that the sum of these two Poisson random variables y and z, right, takes a value small x naught, okay. And the idea is to the question is to find the conditional expected value of y, right, given that. So, before this so as I said in the blackboard lecture, we first have to So for we first have to identify the conditional PMF of y, right. What do we need? We need the conditional, or we need, let me even make it even more clear, we need to find the conditional PMF of x, sorry, y given x equal to x naught. So we need to find this conditional PMF of y given that x was x naught, i.e., right, P of capital Y equal to y given x equal to x naught. This was stated in the Blackboard lecture, right, but the details were not completely given, so we wanted to find this. First of all, of course, we need to identify what values of small y does it even make sense for us to consider. So we will we will call that, of course, as we have always been doing, we will call that as new omega y. So what is given that x equal to x naught, what values x will can y take? Clearly now x is the sum of y and z is a non-negative quantity, and z can take any values from 0 to infinity, right, and independently of y, and but the sum takes a value of x naught. So obviously neither y nor note that neither y nor z can, right, y nor z can take values bigger than x naught. Okay, given that x is taken the value x naught, right, the maximum value that y and z can take has to be x naught. Okay, so they cannot take values bigger than x naught. This clearly means that this given that x equal to x naught, this new omega y is basically going to be the set of values from 0, 1 up to x naught. It cannot take values bigger than x naught, right. So but it can take any value up to and including x naught. So when for example, if you are told that x naught, capital X has taken the value small x naught and capital Y has taken the value 0, that means z must have taken the value also equal to x naught. On the other hand, if you are told that capital X is x naught, but and y also took the value x naught, that means that is only possible when z has a value takes a value 0. So therefore this y, small y, the argument of this, the value for which we are finding this conditional probability, right, has to be in this set a new omega y. So let us go through the calculation. This probability that y equal to small y given that x equal to x naught is basically the probability that y equal to small y and, right, x equal to x naught divided by the probability that x equal to x naught. Okay, so let me, y equal to small y, capital X equal to x naught divided by, this is the standard definition of conditional probability that we all know. Okay, so now here we have both the numerator and denominator. We know that the denominator, right, its probability comes from the Poisson distribution. The numerator, right, is what we have to calculate. Okay, so let me write one more step here, which is basically this is the now the numerator event y equal to small y and x equal to x naught, we cannot easily find it as a joint probability like this, directly like this, but we can write the numerator event as y, the joint event as y equal to small y. Z now has to take the value small x naught minus y. This is the only way in which, right, both this the event that y equal to small y, capital X equal to x naught, right, can happen, right. So these two are equivalent events. So let me just maybe, okay, so these two are the same events, right, equivalent events. And of course you have the denominator, which is exactly from here. So let me write the numerator as, so now then the numerator, the reason why I want to bring in capital Z is I know that y and z, right, are independent. So from the independence of y and z, this probability that y equal to small y, z equal to x naught minus y is basically this joint event is going to be the product of the two y equal to small y multiplied by the probability of z equal to x naught minus y. And now both of them, all these probabilities are now Poisson probabilities, right. So therefore this is going to be equal to, now this y equal to small y is basically e to the power of minus, let me write it with a different color, e to the power of minus lambda 1 into lambda 1 to the power of y divided by y factorial multiplied by this guy out, the guy, the z equal to x naught minus y, that is going to be e to the power of minus lambda 2 multiplied here into lambda 2 to the power of x naught minus y divided by x naught minus y factorial. Okay. So this is the numerator term in the conditional probability up there. Okay. So therefore, so I can now go ahead with the probability that y equal to small y given x equal to x naught. This is what what we wanted. Now it turns out this is going to be so let me also make another point here. This is going to be Poisson. The denominator is from the Poisson PMF of x, right, and that we already pointed out, that was x up here. So we know what we know, this p of x equal to x naught is basically now lambda e to the power of minus lambda 1 plus lambda 2, we know this, right, multiplied by lambda 1 plus lambda 2 to the power of x naught divided by x naught factorial. This also we know from the Poisson distribution, from distribution of x. So this conditional probability now is fairly easy to write out, right. You have the numerator and denominator. I will just do it turns out that this is x, let me x naught factorial divided by, I will the reason why you get this x naught factorial is this thing, it will come in the denominator, this x naught factorial in the denominator will go into the numerator here, and then you have the denominator terms y factorial x naught minus y factorial from the two denominators up here, okay, and multiplied by lambda 1 to the power of y, lambda 2 to the power of x naught minus y, and in the denominator this lambda 1 plus lambda 2 to the power of x naught I am going to split as lambda 1 plus lambda 2 to the power of y multiplied by lambda 1 plus lambda 2 to the power of x naught minus y. I will write this term here as okay, and for what values of y? Clearly for small y in nu omega y, that goes without saying, of course, right. Okay. So this now, which is what all the set of well, maybe I haven't, okay, I have written it here, right. This nu omega y is up here identified for you, right, which is all the non-negative integers from 0 to x naught. Okay. So therefore now this is clearly a binomial probability, right. So why is it clearly a binomial probability? Because this is exactly equal to x naught choose y. Remember this small y is always between 0 and x naught multiplied by lambda 1 by lambda 1 plus lambda 2 to the power of y, small y, multiplied by 1 minus lambda 1 plus lambda 2 to the power of x naught minus y. So you can see clearly that the so y given x x equal to x naught is basically, so this is a binomial distribution, right, we know that this is clearly a binomial distribution, right. So it is clearly a binomial PMF, right, and y given x equal to x naught is clearly binomial with parameters x naught and lambda 1 divided by lambda 1 plus lambda 2. This was stated in the backboard lecture without sufficient derivation. So, I felt that this had to be done, right. So, we have to derive this conditional PMF of y given x equal to x naught. Now, this result is interesting in its own right, in the sense that it can be used in a variety of other contexts as well, not just to find the conditional expectation of y given x equal to x naught. Right. So, it illustrates this interesting interplay between the binomial and the Poisson distributions, right. And what have we done here? Just recall what we did. We took two Poisson random variables y and z, right, which had parameters lambda 1, lambda 2. We added them to form x. So, x was itself also Poisson parameter lambda 1 plus lambda 2, and then we conditioned on x. We said let x take the value small x naught, right. Which was again from the Poisson that Poisson distribution of capital X, and then ask for the conditional distribution of y given this event x equal to x naught, and so that turns out to be binomial with parameters x naught and lambda 1. So this is the P of the binomial distribution. This lambda 1 by lambda. So this is the P of the binomial distribution of this binomial PMF. And so then it is a very simple matter to identify that the conditional mean of y given x equal to x naught is exactly x naught lambda 1. Just we know that it is NP, right. We just multiply this n and we multiply it with the p, and we get this x naught lambda 1 by lambda 1 plus lambda 2. And exactly by symmetry, expected value of, or let me say okay, I will just say write it here, expected value of z given x equal to x naught will be x naught into lambda 2 divided by lambda 1 plus lambda 2. The only difference here is the numerator lambda 1 becomes lambda 2. So, y is x naught lambda 1 by lambda 1 plus lambda 2, and expected value of z, the conditional expectation of z given x equal to x naught is x naught lambda 2 divided by lambda 1 plus lambda 2, and what is z given lambda 1, the distribution of z given x equal to x naught is going to be binomial x naught and lambda 2 divided by lambda 1 plus lambda 2. Note that, right, both whether if you take that kind of a fraction for non-negative lambda 1 and lambda 2 or positive lambda 1 and lambda 2, right, the lambda 1 by lambda 1 plus lambda 2 is going to be another positive number which is between 0 and 1. Okay. So, this is basically what was done in the blackboard lecture, right, and I just wanted to go through the derivation properly so that you people do not feel shortchanged, right. I wasn't very happy about just simply leaving it out, so I wanted to take the trouble to put it I wanted to take the trouble to derive it properly so that there is no confusion about it. So, right, and remember, if you are given a binomial PMF and you are asked to find the mean value, you just simply multiply the n and the p, right. And so let me also write here that this is the n. What is this x naught in this case? It is just the n of the binomial PMF. Let me say n and p of the binomial PMF. So, the n is x naught, and in this case p is lambda 1 plus lambda 2, and the mean value of that p or the expected value of that PMF is n into p, which turns out to be the product of those two numbers x naught and lambda 1 and lambda 1 plus lambda 2. Okay, with this I will stop this. I will stop and take up the next example in the next maybe the next video segment.